loudspeaker from a bad loudspeper, or perhaps more importantly, a good loudspeaker from a truly great loudspeaker. So in the next hour, I'm just going to run through what I do, why I do it, and what it means. So my first slide. These are the typical terms we use to describe sound quality. Accuracy, how good it is, how neutral it is. Does it have enough bass? Does it have enough treble? Is there coloration? Is there distortion? How clear is the picture the speaker presents? Is it transparent? The soundstage that the pair of speakers produces, how much width does it have? How much depth? How deeply can you hear into the recorded image? Is the image precise? Or are sonic objects within the soundstage blurred and diffuse? Dynamics, microdynamics, can it preserve more small detail when the overall level is loud? Macro, how loud can it go? Pace and rhythm, do you get the feeling that the music has vibrancy? Or is it lagging, is it sluggish, is it slow? So those are how we describe sound quality. These are the measurements I do. And the first thing to notice is not one of them correlates with any of the things I've just described in sound quality. They are all measurements I do because they're possible. They take one parameter plotted against another, voltage versus time, voltage versus frequency, phase versus frequency, frequency response versus on and off axis, nonlinear distortion, cumulative spectral decay performance. Does the sound, how does the sound linger on after it should have stopped? And not one of these correlates with any of the previous ones in the previous slide. These are how we describe sound. These are how we measure sound. And yet there's no correlation. What you have to remember is that we can only measure what is possible. The ear and the brain basically integrates all these measurements simultaneously to come up with a value judgment, good or bad or great. So in the next, as I said, I'm going to take you through how I do the measurements and what they mean. Okay, voltage sensitivity. This is the first thing I do in every measurement. How loud will a loudspeaker play at a specified distance for a given voltage? Often people call this efficiency, but efficiency is the wrong word, because efficiency is power out for power in, and we never look at power out when it comes to a loudspeaker. We're looking at the sound pressure level, which is equivalent to a voltage. So what I do is measure voltage in and sound pressure level out. Loudspeakers tend not to have a flat response, so when specifying sensitivity, manufacturers tend to be optimistic. If it has, say, a peak in response of 5 dB at 1 kilohertz, well, that's the level they'll pick to measure and quote their sensitivity. When I prepared this speech for the AES, I reviewed 261 loudspeakers. As in the introduction said, I'm not under 750, but basically it's the same information, nothing has changed. Mean sensitivity for a loudspeaker is 88 dB, median is 85, and in other words, 85 dB splits all the models halfway. But the mean is 88, but given conventional engineering at a conventional price, then an 88 dB sensitivity is what you will get. If it's significantly more than that, then, and if the manufacturer is not being optimistic, then you're looking at something like a horn speaker or a direct radiator speaker with an enormous magnet to give you the motor. But 88 is about right for a typical domestic loudspeaker. The impedance. This is how hard is the loudspeaker to drive, measured in ohms. I publish a graph every month for every speaker which has impedance magnitude in ohms and impedance phase in degrees. And it's also a good diagnostic tool to determine are there fundamental problems with the loudspeaker. Does it have unnecessary resonances? The problem is it varies with frequency, and also if your electrical phase is out of phase with the amplitude, you have a speaker that can be extremely hard to drive. Here's a typical impedance plot. I'm looking at right away. There's a single peak in the bass, that means it must be a sealed box. That's the peak is at the frequency of the box tuning frequency. There's a really bad glitch there in the impedance magnitude trace. That says that there's some kind of speaker cabinet resonance going on at that point, which may or may not have audible consequences, as you'll hear later. There's a glitch right there, about 25 kilohertz. So I know immediately that this is a speaker with a metal dome tweeter, and that's the frequency of the metal dome's first resonance, which is when in the middle part of the dome is radiating out of phase with the outside. I call it the oil can resonance, because if you ever had one of those metal clickers, that's the sound it makes. It's at 25 kilohertz, so it's above the audio band. It shouldn't have any audible problems. However, that is not always the case. If you're playing CDs, that resonance will never be excited because CDs cut off at 22K, and a resonance needs to be stimulated for it to have an audible effect. However, if you're playing an LP with the speaker, with a moving coil cartridge, you will hit that resonance with energy at its own frequency, and it might ring and cause the speaker to sound a little, dump back into modulation products in the audio band. Here's the phase of that speaker. Again, you have this characteristic trace in the bass, a single peak and dip, and then there's the little red glitch showing there's a cabinet resonance and a glitch showing the tweeter resonance. The thing to note is that at the frequencies where you have the most extreme phase angles, which is where basically the speaker is asking for large amounts of current without much voltage, they never coincide with the lowest magnitude. So you get a little bit of a free ride there. But where you do have a combination of high phase angle and low impedance, it basically gives you a speaker which is maybe 2 or 3 times harder to drive than its impedance specification will suggest. There's a histogram of all the speakers I had measured back at the end of the last century. The mean is 8.6 ohms, the median is 9.25. Speakers with an impedance less than 3 ohms are really rare. Speakers with an impedance more than 15 ohms are very rare. They all cluster around about between 7 and 10 ohms. If you look at the minimum impedance values, the mean and the median is those 4.3 ohms. So if you have an amplifier that can drive 4 ohms without any problem, you won't have any drive problems with your speakers, unless they are a pathological example, and you can read my reviews to see which they are. In the time domain, the impulse response carries all the information you need to characterize a speaker's performance. I'll play you one. Okay, this is a pulse. Where is it? Okay, this is the sound of an impulse response. An impulse. Go ahead. Yeah. I can hear it. Is it music because I'm on the mic? I'll give you some pink noise just. Let me play the pulse again. It's kind of illustrating the point I'm going to make, is that. There we go. It's really hard to hear. It's over almost instantaneously. Although that is a full-scale, single-sample pulse, it carries so little energy that it's difficult to hear. Because it carries so little energy, it's very difficult to use as a measurement system. That's what it looks like, a single up-down pulse, and its width is characterized by the sample rate of the system I'm using. This was a 44.1K, so that width is just over 11 microseconds. So very, very hard to hear. Okay, so what I do is instead of using a pulse, which is difficult, I use what's called a maximum length sequence signal. I'll play you the signal I use. This is the Melissa signal. It sounds like random noise. Actually, it has exactly the same spectrum as the pulse that I just played. The advantage is it's loud, has a lot of energy, and You can therefore carry out measurements in a relatively noisy situation, which, in absolute terms, real rooms are. What the computer does, it feeds that signal to the speaker. Microphone picks it up, and the computer then performs what's called a cross-correlation operation. It looks at the output of the microphone, it knows what it's sent to the speaker, so from that it can calculate the impulse response. And here's a typical result. There's the impulse response calculated by Melissa from a maximum length sequence. It doesn't look much like the original pulse. That's the original pulse. That's what the speaker does. And the change characterizes the entire performance of the loudspeaker. There's a quick up-down from the tweeter, followed by some ringing and a laser up-down from the lower frequency units, slow decay. There's my first reflection from the room, that little up-down pulse there. More reflections from the room afterwards. So, how do I extract meaning from that? Okay, the impulse response on its own is difficult to interpret. It's dominated by the tweeter output. So what I look at first is the step response. There's a perfect step. The voltage is 0, rises up to an arbitrary level, and stays there. A speaker cannot reproduce a flat response at a DC offset, because all speakers are high-pass filters. So here's a good step response from a speaker. This, I think, was a quad. The speaker immediately rises to the level of the input. There's a little bit of nonsense going on there. Resonances, unflat response, and then the sound smoothly decays back to the timeline, overshoots, and then there's some undulations. Eventually it'll return back to the timeline. That's a really good step response. Speakers that do that, perform that well, are quads, the old Spiker TC50 and Angelus, all the Vandersteens, some other electrostatics, and now I'm running out of examples, because 99.9% of speakers in existence produce a step response which looks more like that. Well, what's going on there? Okay, well, there's a little sharp rise there. There's a you can see it, there's an inverted step there, and then there's another slow rising step there, followed by a decay to the timeline, which is actually undulating. The undulations have said there's a resonance of some kind. There's the room reflection again. So this is obviously a multi-way speaker. There's the tweeter, sharp positive going step, followed by some ringing. And this is the ringing from its metal dome that I talked about earlier. There's the mid-range unit step. You can see it's in opposite polarity. Instead of the step going up, it goes down. Then there's a huge undershoot, and then it slowly decays, but with some oscillation suggesting resonances. So already I know that this is a speaker where the tweeter and the mid-range are out of phase with one another. Here's the woofer step response. Slow rise, slow decay. Woofer's step responses are dominated by the crossover. When people talk about fast woofers, it's an oxymoron because there's really no such thing. A woofer can't be fast because if it's connected through a crossover. However, when people say fast or slow woofers, they're talking about other aspects of the performance. So, again, all those individuals, the woofer, the mid-range, the tweeter, add up to that, the typical step response. What's important to note, and I make this point often in the magazine, is the decay of each step smoothly blends into the rise of the next unit. So the tweeter goes up, decays, and its decay smoothly blends with the mid-range step. The mid-range decays and smoothly blends with the woofer step. This means that although the drive units are connected out of phase, the tweeter's in phase, the woofer's in phase, the mid-range is out of phase, actually in the frequency domains, I'll show you later, their outputs add. And this is will give a flat response. It sounds a little unintuitive that you have the mid-range out of phase that gives you the best frequency domain response. But what you have here is that all speakers, other than a few, have a flat baffle. The tweeter is physically shallower than the mid-range. So the tweeter's output will always arrive at the microphone or your ear before the mid-range. So what you do is with the crossover, you're actually fiddling with these arrival times so that you get this smooth blending. I here's a pathological example of a speaker I reviewed a while back. Here it's a four-way speaker. You have a super tweeter, which is the red. You have an ordinary tweeter, which is the blue. You have a mid-range unit, which is the green. And you have a woofer, which is the black. And you look at that and you think, well, I don't get that smooth blend at all. The tweeter arrives first, because it's shallower. Then you get the super tweeter. Then you get the tweeter arriving, but its decay doesn't blend with that. Its step doesn't blend with the super tweeters. Then the mid-range arrives, the green, and at the time the mid-range is going upwards, the tweeter is going downwards. So actually, the tweeter and the mid-range are out of phase. They're not adding properly as they should. And then, when the woofer comes in, the mid-range is going down. So the mid-range is fighting the woofer. So I can tell without even looking at the frequency response that there's something dreadfully wrong with this speaker. The drive units are not adding at all. In some, they are actually working against one another. Okay, frequency response. There's only one way to do this, and spent a large, expensive anechoic chamber using a swept sine wave. That is beyond the reach of organizations like Stereophile. And there's only one organization which does use it, which is give them a benefit, but give them a good plug. Soundstage magazine does do measurements in an anechoic chamber, one provided them by the Canadian government. So we need a magic bullet. I've already captured the impulse response using Melissa. So, the impulse response, as I said, contains all the information you need to characterize a speaker's performance. How do I turn that into a look at what's happening in the frequency domain? A Frenchman called Fourier worked this out 2 centuries ago. He was, of all things, he was looking at transfer of heat in heat conduction. But this transform, the fast discrete Fourier transform, usually called the FFT, takes time domain information and then transforms it into frequency domain information. I'll show you. To show you how it works. I'll come back to that. So okay, so I've taken my frequency response. I look at just the anechoic section. Here's the room reflections. So what I do is I just look at the point from time 0 to just before the first room reflection. I then stitch the end of the impulse response to its beginning to produce a continuous wave. Then when I apply the fast Fourier transform, I get a frequency response at the at frequency intervals which are the inverse of that time period of the synthetic wave I've created. Problem is, go back to an earlier slide, I lose resolution in trade-off this frequency resolution because the steps in my response are governed by the length of the window I've created. That distance is 8 milliseconds. So the first, in the FFT transformed frequency response, the lowest frequency point is going to be 1 second divided by 8 thousandths. So it's going to be 1,000 over 8, what's that, 125 hertz. So I have no information below 125 hertz. The next step in that, because it's a waveform, is going to be the second harmonic of 125 hertz, 250 hertz. The next one, 375 hertz, and so on. So at low frequencies, I'm not getting really good performance. And this is because I've had to window the impulse response. Show you what's happening. Here's my microphone, here's my speaker, sound emitted by the speaker. The blue path is the direct sound from the speaker, from the tweeter. The red path is the reflection of the sound from the ceiling and the floor. And I can show you here that the red path is longer than the blue path. So when I'm measuring speakers, I try to arrange the geometry of my measuring situation so that the difference between the red path, which is from the first reflection, and the blue path, which is the direct sound of the speaker, is as long as possible. When possible, I do it outside. I raise the speaker on a really high stand. This is around 8 feet above the ground. I use a very high microphone stand. I use a long tube from the mic stand so that the reflection from the microphone stand itself occurs after the reflection from the nearest surface. So I'm trying to extend that time window to get as low a frequency information as possible. As I said, here's a typical result. Frequency, as I said, the frequency response has points that are separated in time. So in frequency by the reciprocal of the impulse response, the gated impulse response. So I don't have a lot of resolution here until I get to about here when the points get closer together. And up here I have tons more resolution than really I need, as you can see by the fact that the smooth curve actually has little ripples in it. This is the speaker I showed you the impulse response earlier, and the impedance. There's the tweeter resonance around 25K. It's above the audio band, but it's really severe. There's something going on there in the mid to the low treble, some kind of peak. Either it's a resonance from a woofer cone misbehaving or some other point. But the overall trend is quite flat. Just to show you why I go to such elaborate lengths with a long copper tube as my mic stand. These are reflections in that response if I'd used a normal mic stand. This is the effect on the frequency response from all the hardware, the clip, the clamp, everything. So I move the stand back in time. Yeah, I use a long tube, so the reflections from all this hardware are out of sight. Okay, what happens in the bass? With this gated impulse response, I don't have any information below 125 Hertz or so. So Don Keel, who did speaker reviews for Audio Magazine quite a long time, now works as a consultant and actually has speakers here at the show which are intriguing as they have eliminated the floor bounce, the bounce of the sound from the floor. When he was a student, he developed a near-field technique. What you do is you just basically put the microphone right up against the woofer or the port. And what you're doing, the direct sound from the loudspeaker is then so much larger than any of the reflections of the sound from in the room that you're basically looking at the anechoic response. The problem is, you always get a bump. This is a speaker which actually measures flat if you're in a true anechoic chamber, but the near-field response gives you this characteristic bump in the mid to upper bass. And this is because when you use the near-field technique, it assumes that the speaker is infinitely big in all directions. And that, of course, is not true. But what you're doing is basically then, because it's infinitely big, then it gives you, in theory, a 6 dB rise in response at a frequency governed by its physical size. So people ask me, why don't you correct for that in your published graphs? It's difficult to correct for it. It's going to depend on the size of the speaker. You make assumptions that may or may not be true. I would rather show the basic near-field response and explain that it has this exaggeration rather than guess at what it would be. If you think about it, an anechoic chamber where there are no reflections and a sealed and a near-field response where there is no reflections. The anechoic chamber has no reflections at all. The near-field response assumes the reflections are infinitely low in relation to the direct sound, are two extremes. And I therefore show if that flat speaker went like that and the near-field goes like that, there's performance in a room where it's not going to be an anechoic chamber, there are going to be boundaries relative, it's going to be somewhere in the middle. So I prefer to show that raw performance and interpret it. That was a sealed box. This is what happens with a reflex design. Well, here you have two radiators. You have the woofer, which is this curve, and you have the port, which is this curve. And they add to give you this curve. A reflex woofer always has a minimum motion notch. That's where the port is giving all the output. But the port resonance is so strong at that frequency, it's tuning frequency, but it's holding the woofer still, and all the output's coming from the port. Below that frequency, the port and the woofer are actually out of phase, and you get a fast roll-off compared to the faster roll-off with a reflex than you do with a sealed box, which has a single roll-off. So reflex designs give you more bass above the port resonance and less below. And you can get to a situation where a little Sealbox speaker like an LS35A gives you more low bass in room than a larger reflex design, purely because it's rolling off at a slower rate. Here's a good amplitude response. Flat trend, some peaks and dips, but peaks are balanced by dips. It's overall neutral. And then you have the tweeter resonance, and you have bass, which has the near field bump, but it's actually probably flat down to about there. It's a good speaker. Here's one which is by no means a good speaker. You have, okay, the bass is a little underdamped. This rise is not as big as it was with the other. But then at the top of the mid-range, you get these peaks. Then you have horrendous suck out in the upper mid-range low treble, followed by peaks in the mid-treble, and then the tweeter, ultimately its output is about 5 dB too low. And I'll come back to this speaker, because the designer here has problems that he's trying to solve in the wrong way. We're resulting in this region, the tweeter and the woofer are out of phase. They're fighting each other, the result is no output. And here you have some peaks, here you have some peaks. There's resonant problems going on, which the designer can hear that there's some problems in the treble, but his solution is to take the tweeter down by 5 dB, thinking that's the problem. Except, as I will show you later, this problem here isn't due to the tweeter at all, it's the woofer. Here's the speaker I showed you earlier with that really strange step response, where all the drive units seem to be fighting. And you can see that between the woofer and the mid-range, there's a huge hole because they're out of phase. Between the mid-range and the tweeter, there's another huge hole because they're out of phase. And you have a hole between the tweeter and the super tweeter because they're out of phase. You think, well, why would a designer do that? Why would a designer make a speaker which is deliberately wrong? Well, this is one of the mysteries with speakers. I listened to this speaker, and so did my reviewer. And I heard it as having a hole in the lower mids and a hole in the low treble. He heard it as sounding great bass, detailed mid-range, and a relatively flat high treble. And this is one of the difficulties when you have speakers which are not flat. How do you describe the sound? We came up with completely different sound descriptions. However, we are describing the same thing. We are latching onto different aspects of this really unflat response to describe the sound. So when you see reviews of speakers and they appear to differ in their description, they may actually be talking about exactly the same thing, but depending on the music they use, they are latching onto different things. And it's a bit like one of those visual things where you have, is that a vase? No, it's a woman's face. And you kind of flip between the two, depending on how you look at it. What happens off axis? Now, when you listen to a speaker in a room, I've just shown you the sound directly on axis, but the sound you hear is also affected by what happens off axis. Unless you live in an anechoic chamber or a field, the reverberant field in the room is going to affect your perception of the speaker's quality, and it can also affect the imaging performance. This is a typical off-axis behavior. The on-axis response I've plotted as a straight line to make the differences more clear. As you go up in frequency, the speakers, at low frequencies, all speakers basically are omnidirectional. They're radiating equally in all directions, even when the woofer's on just the front. There's as much energy to the sides and the rear. As you go up in frequency, the woofer gets more and more directional. It's the laws of physics. The larger the radiator, the narrower its dispersion will be. And here, just before the crossover to the tweeter, the woofer is giving out very little energy to the sides. When the tweeter comes in, the tweeter, of course, is much smaller than the woofer, and has relatively wide dispersion. So you get this flare at the bottom of the tweeter's passband, a gully at the top of the woofer's passband. Well, how does that sound? Well, if the speaker was flat, it would sound uninvolving due to this huge lack of energy in the reverberant field. And maybe a little bright because of this excessive energy at the bottom of the tweeter's passband. If I go back to its frequency response, has some peakiness in the region where the off-axis response has a gully. And in a typical room, they will tend to work against each other. And when you read about designers voicing a loudspeaker, a lot of what they're doing is adjusting the crossover point and the level of the tweeter to give you that kind of balancing act. So in a typical room, two problems counteract each other to give you an overall perceived neutral response. Here's a good lateral off-axis behavior. The speaker, again, I plotted the on-axis as a straight line, but it's just to bring out the differences more clearly. But as you go up in frequency, the speaker maintains its dispersion to quite a high frequency. There's a little ridge there at about 5K, which is due to probably an on-axis gully filling in slightly. And then above 10 kilohertz or so, it gets very much more directional. The speaker's output to the side falls off. But this speaker is very good dispersion. Often you will find with a speaker like this, a typical 1-inch dome tweeter will always get more directional above 10K because its wavelength of sound is becoming equivalent to its own dimension. So a speaker like that you'll see often has a slight rise at the top end on axis. Again, balancing the rise in top end response against the lack of dispersion above 10K, giving you an overall flat response. Vertically, you can never get smooth with a normal speaker which has vertically arrayed drive units. You always get problems. So here's again, the tweeter axis response is a straight line. Below that, you get some slight peaks due to the fact that the tweeter and woofer are adding more in the crossover region. Above that, you're getting gullies developing because you're getting suckouts due to the fact that once you move above the tweeter, the outputs of the tweeter and woofer are out of phase. Basically, I always measure speakers on the tweeter axis. Almost always that's the design axis. The axis the designer has intended you to listen on it. And almost always with a speaker like this, as you stand up, you get this hollow sounding suck out in the crossover region. So when you come to a show like this and you're standing up at the back of a room listening to a speaker, you're not going to hear it at its best. You really do need to sit so you're on the tweeter axis to hear the sound the designer has tried to get. I do in-room responses. I do them in my room, I do them in Michael Fremer's room, I do them in Wes Phillips's room. Basically rooms where I can easily get to. I do. This kind of measurement gives you an integration of the direct sound of the speaker and what it's doing in the reverberant field. I take 20 measurements in a grid, like 36 inches wide by 18 inches deep, for each speaker left and right individually, and I then just average them with a slight weighting towards the position of the center of the grid, which was where my ears are in my listening chair. And this gives you a thumbnail which actually correlates pretty well with the balance you hear. This speaker, below 300 hertz or so, there are always some residual effects due to the room acoustics that are not removed by the averaging. However, you can see that this sealed box speaker, which is an LS35A, there's a dip there in my room, which is 50 hertz. There's a peak there, which is 32 hertz. This is typical of my room. I can never get rid of these problems. A little too much energy at 32 hertz, because that's the frequency of the diagonal resonance in my room, and a lack of energy at the listening chair at 50, which is an anti-resonance, which I can only get rid of by moving my seat backwards and forwards. But I kind of average. I get my listening position to give you a good balance between those two. But the little speaker extends actually remarkably low in frequency. The red trace is a reflex speaker we reviewed last year. And actually, it's rolling off below 120 hertz. There's a slight peak there, which is it's being reinforced. Its reflex, its port tuning is coinciding with the 63 hertz peak resonance in my room, but then it's rolling off quickly. So the LS35A, which is about a third the size of the reflex speaker, actually gives you more low bass. The LS35A has a slight lack of energy there and a peak in the low treble. This kind of response shape where you get a little peak about between 1 and 2K and then a flat, always sounds a little nasal like that. It's characteristic. And yet any LS35A does sound nasal. But the reflex speaker doesn't have enough mid-range energy, has way too much energy at the top of the mid-range before then having basically a flat travel. And this speaker sounded considerably more nasal than the LS35A, and really, I thought, unacceptably coloured. So it puzzled me that the speaker got quite good reviews elsewhere. not by our reviewer, he heard that, he didn't like that. Everything I've discussed so far is linear distortion, changes in amplitude and phase. I don't measure non-linear distortion, what we call THD, or harmonic distortion, or intermodulation distortion, because basically there's a real correlation between speaker size and price and distortion. The smaller the speaker, the higher the distortion at the same sound pressure level. If you want more sound pressure level, you have to buy a bigger speaker. I do tend to do measurements when I find a speaker which is particularly good, as I did in the quad review in the May issue. This is a speaker that has lower distortion at a typical level than almost all tube amplifiers. However, measuring distortion without an anechoic chamber is difficult and awkward, so that's why I don't do it. Distortion tends just to limit dynamic range. It sets your maximum playback level. You can't expect a little bit of a pair of PSB Imagine Minis this big to sound as big as JBL's this big. But that's, a choice you make. I mentioned earlier the cumulative spectral decay plot shows how quickly the loudspeaker's output decays after being excited by the pulse. It's really good at revealing resonant behavior. Again, the problem is the region which is most of interest is in the mid-range, and that's where I don't have a lot of resolution because of the FFT technique. Here's a typical cumulative spectral decay plot. It's the one of the speaker whose dispersion and frequency response I showed earlier. You can see it with that peak where the designer was trying to compensate for in the dispersion. Actually, there's a resonant peak. The sound lingers on just at that frequency as the sound decays. Similarly, the tweeter, the oil can resonance of the metal dome rings like a bell and keeps on going. But it's above the audio band, so hopefully it won't be an issue. But this one, this is very common, this kind of behavior. This is where the sound, the woofer cone has a surround, a rubber surround of some kind. And this is a resonance due to the fact the sound travels out from the voice coil, hits the surround, and comes back through the cone back towards the voice coil. And you get a standing wave set up at this very characteristic resonance frequency between like 1 and 3 kilohertz. You often see that. Here's the cumulative spectral decay of that awful speaker I showed you earlier. There's the suck out and the crossover due to the woofer and the tweeter being out of phase. But there's this horrendous resonance here, which rings for almost 3 milliseconds. And as I said, the designer could obviously hear there was something going on, because he would have heard this as brightness and hardness. So what he was doing was reducing the level of the tweeter to try and reduce the brightness, except the problem is actually in the woofer. So he's leaving it, he's not affecting the resonance, it remains there, ringing to its full extent, but the tweeter is reduced in level. So you get a speaker which is simultaneously dull, because the tweeter is too low in level. The speaker is uninvolving, because you have the tweeter and woofer crossover, not optimal, they're out of phase. And you have this horrendous resonance which will outbrag brightness and hardness. So a speaker here sounds dull, bright, hard, and uninvolving. The mystery is that this speaker was made a reference in its price marks by the editor of another publication. And I just couldn't believe it. It's like, well, why would he do that? What is there possibly in this speaker's performance that attracted him to it? And I couldn't think of it at all. Okay, here's the idea. Cumulative spectral decay plots. Here I've been looking at the far field responses of loudspeakers, but of course I can apply it to anything that I take, that I can take an impulse response. And back in the end of the 80s, I looked at using impulse response and cumulative spectral decays on speaker cabinets. Speaker cabinets radiate sound. They're never very good at enclosing the sound between them unless they are heroically designed. Magico, people like that. You can see how heroic their speaker cabinet engineering is. So, how do I detect if a speaker cabinet is well behaved or not? Well, the obvious way is just to wrap it. See what kind of noise it makes to you. So, I'll play you a few impulse responses from speaker cabinets. These are some of the, here's a good one. This is a side panel of a small monitor. You can hear that it sounds a bit like, you can hear the knuckle rap, and you can hear there's a ring after it. Play it again. Play you another one. This is a different speaker. Wow, I rap with my knuckle and it produces quite a loud ringing noise, an octave higher than the earlier one. Here's another one. Lower in frequency again. Now, how audible are these resonances are? Generally, the higher in frequency they are, the less audible they are because they don't last as long, and the frequency of that resonance may fall between the gaps in music. I mean, in Western music, with A equals 440 Hertz, there are quite large gaps as you move up in frequency between the notes. So if you're only playing string music, it's possible you will never excite that resonance. On the other hand, if you're playing drums, you probably will. So I'll play you that. Let's see if I can. Here's a particularly interesting one. This is not a cabinet resonance, this is a port resonance, but the idea is the same. You can hear the boom from the port, but also you can hear a high frequency aspect to it as well. And if I play you a recording I made of that speaker, okay, okay, so this is a port on the rear panel, and okay, there's the impulse response of a cabinet resonance. You can see it rings like a bell. I played you some of those. There's the cumulative spectral decay of that impulse response, and you can see that there are several resonances around. And here is the sound of a speaker that has a really bad, uncontrolled resonance in the mid-range. All I did was put the microphone behind the speaker and play a piano recording. You can hear that the piano is exciting the resonance on some notes, but not others. Okay there. And then off the resonance goes again. And this is what this measurement shows, that if there are resonances, they will be excited. And the trick of the designer is arranging that they're not, but with music, they won't be excited as much as they could be. Often you see like some of the tuning tips, like in the old days, putting a Mpingo disc on the side of a cabinet. Wow, that made it sound better. Not because the Mpingo disc is magic, but all it's doing is shifting slightly the resonance frequency to make it a little less audible. Is that? No. Okay. Okay, so here's to sum up the measurements I do. On-axis amplitude response, off-axis behavior, nonlinear behavior, cavity behavior, the time coherence. As I said, that's rare in speakers. Not that it matters, because the ear can't detect, in theory, anything which occurs between about a 7 or a 10 millisecond time window. So if the fact that the tweeter arrives at the microphone half a millisecond ahead of the mid-range, you're not going to hear that. There's an actually interesting fact when I was preparing my AES lecture. One of the things I found was that we all experience the world about a tenth of a second after it occurs. That's the processing time that our brain takes to process information reaching our ears, but also our eyes. And in fact, we all compensate for that without even realizing it. But we're all seeing the world about 100 milliseconds as it was in the past. And you can actually do psychoacoustic tests to show this. For example, if I play you a very low-level sound and follow that with a high-level sound about 20 milliseconds after, the high-level sound masks the low-level one, even though it occurred earlier in time. Which is kind of weird if you think about it. How can things happening later affect your perception of things that happened earlier? And it's because of this latency of the ear-brain processing. It's something, it fascinated me to find that out. I never thought about it before, but Your ear and your brain takes a finite amount of time to process the information reaching it via the senses. You never think about it, you think it's instantaneous. It's not. Okay, time coherence, sensitivity, how loud do the speakers go, and impedance, how hard are they to drive. Okay, golden rules about measurement. No one measurement tells the whole story. What you hear always depends on more than one measurement. Measurements, as I said, we choose parameters because they're easy to do. Voltage versus frequency, voltage versus time. With cumulative spectral decay plots, we're choosing 3 parameters: frequency, voltage, and time. But even so, that doesn't give a complete picture. The complete picture only comes from all the measurements together. And fortunately, God gave us, or our Creator gave us the ability to do that, and it's called our ears. Our ears take all that information, process it simultaneously with the latency I mentioned, and give you the idea. So, performing a measurement involves subjective choices. I've had to decide what measurement to do, what set of measurements to do, and maybe I'm overlooking something. Maybe there is something I should be measuring that I'm not. And as you look at Stereophile's reviews over time, they do evolve, particularly when it comes to digital and amplifiers. So the very fact you're making a measurement doesn't make it objective, because you've chosen what to leave out. All measurements tell lies. I remember once when I first got Melissa, and one of my other reviewers was using it, and he gave me a response, a cumulative spectral paper, and I said, I don't believe this. I don't believe this. This is perfect. And he said, well, it's a really good measurement. So I looked at it, and actually the microphone power supply wasn't turned on. So it looked perfect. It just happened to be completely wrong. Measurements can't tell you, they can tell you how a speaker sounds. Everything I've talked about is, how much here, how little there. What they can't tell you how good it sounds. For that, you have to rely on your ears. And that brings me to, to your own ears be true. If I gave you a speaker and I said, this measures so perfectly and you hate the sound of it, then your ears are what you should rely on. To thine own ears be true is the golden rule for all listeners, all reviewers. Don't fool yourself into trying to hear something as good when it's not really bad. Or vice versa, if it's bad when it's really good. You have to educate your ears. One tip is, listen to people's voices on the speaker. We're all familiar with our own voices, with the voices of people we know. Does it sound right? Is there something going on? Is it like that piano recording where there's something going on, like a little xylophone inside the speaker being banged every time the voice hits a certain note? Yeah, if you don't enjoy your music, something must be wrong. You sit there and you tense up and feel there's something wrong, something is wrong. Okay, so golden rules. There they are. Be to thy own ear be true. And no matter how good the measurements, if you don't enjoy the music, something is wrong. Okay, so that's the end of my prepared presentation. I'd love to open it to questions. Sir?
Thank you very much for presenting, John. I'm wondering if your slides are available for us to peruse on your time, maybe you send us a file?
All the slides I presented, which almost all are in some articles I published on the website about 10 years ago. But I'm hoping to be able to make the video of this presentation available, including the slides, sometime later in June or early July. Ma'am at the back.
I'm not an audiophile. I'm not the wife of an audiophile. And one of the things that we often talk about is the shape of the speaker and how it affects the sound. And I'm talking instead of the traditional box,
Yeah.
you have maybe an oval, or you have a more exotic shape.
Well, what you're dealing with is, if you put a drive unit on a flat baffle, where the baffle ends, you get this sharp discontinuity between baffle and no baffle, and you will get reflections of the sound from the drive unit reflected back. You get resonances set up, standing waves set up, just as in the example of the woofer surround combination I mentioned. When you round that corner, then what you're reducing the level of that reflection. Every time you see a discontinuity in a loudspeaker, think reflections. Think there's going to be an effect on the sound somewhere. So when you round it, what you're doing is reducing those reflections. If you round it in a certain profile, you can actually get rid of the reflections completely. And if you look at various egg-shaped speakers, that's what they're trying to do, is get rid of those reflections, get rid of the resultant standing waves, result in a smoother dispersion and a smoother on-axis response. So that's why you see those kind of shapes. On the other hand, of course, they're more expensive to make, they're more expensive to develop. So, it's no pain, no gain.
Okay, and the other thing he says is that one of the reasons they make these odd shapes is for spouse appeal. Because
Has anyone come across that?
when we first got together, he had Freed speakers that were 5 feet tall.
Yeah.
And frankly, I was terrified of them. They were in his dorm room. And, now we have 7 foot tall. 250 pounds each, okay? And I'm just hoping the next ones won't be 1,000 pounds and 10 feet tall.
Yeah. The real problem with loudspeakers, it's very hard to make, the whole different thing about spouse appeal is, why do I have to have speakers which are out in the room? Unfortunately, that's where speakers work the best. If you put the speakers against the wall or in the wall or in the corners, then the room is affecting the sound of the speaker to such a severe extent that it's very hard to get consistent good sound. And that's just one of the problems of physics. It's the way it is.
What about panel speaker measurements?
Panel speaker measurements. I didn't mention panel speaker measurements at all. If I go back to an early slide. Okay, there's my speaker measuring setup. There's the floor. As I said, I try to arrange it so that the red distance, which is the path the directions take, reflections take, is very much longer than the direct sound. With a panel speaker, if you think about it, it's big. So it's going to be tall. And where you have, it's radiating from all over its length. So it's actually impossible, practically, to get this microphone far enough away that you're going to be both close enough that you don't get effective reflections, but far enough away that you're in what's called the speaker's far field. The hidden assumption I didn't talk about is that this distance is always much bigger than the size of the loudspeaker. With 2 ways and 3 ways, typical dynamic speakers, that's always true. With panels, it's not true. And what tends to happen is you get a sloping up of the response measured in this way at low frequencies, exactly as if it were a near-field response measurement, because it is a near-field. The speaker's huge and you're not far enough away from it. The other thing that panel speakers have, and I've discussed this with Wendell Diller at Wendell Diller of Magnapan on WAP. There's a cumulative spectral decay. Okay, if I look at a panel speaker, cumulative spectral decay, other than this one resonance here and the tweeter resonance there, this is a well-behaved speaker. The sound drops off very quickly. A panel speaker looks terrible. This whole region in a panel speaker is full of resonant hash in a cumulative spectral decay for a panel speaker. And I don't think it's, I thought about this a lot. Is it showing resonances? I don't think so, because panel speakers don't sound resonant. Maybe what it is showing the multiple reflections of the sound from all the different radiating elements of the panel. In other words, the panel is large and it's moving backwards and forwards. Maybe the average position of the panel is moving backwards and forwards due to electrostatic drive or magnetic drive of the magnet painter. But actually, maybe what is really happening is the average position is moving uniformly, but the panel is shimmering as it moves backwards and forwards. And what the cumulative spectral decay plot is showing the result of that shimmering as all the hash in the decay. The ear doesn't hear it because, if you remember, as I said, the ear integrates the sound that arrivals. And because it's relatively uniform across the audio band, this is an example, I think, of maybe a measurement that's telling lies. It makes panel speakers look much worse than they really are. But I'm still thinking about that. That's something which I haven't resolved.
And just a quick follow-up, most panels are also dipole radiators.
Yeah.
So the distance from the back wall and the corners, the ceiling, the floor, you've got all that back information bouncing back off and coming back towards you.
That's true. And in fact, I mean, if you get a panel speaker and you put pink noise through it, just play you some pink noise. Yeah, so I mean, if I play you pink noise, with play that in a panel speaker, sit in a listening chair and get a friend to move the speaker backwards and forwards, and you can hear a formant quality in that pink noise, like, going on as you move the speaker due to the cancellation between the back wave and the front wave. And what you need to do is to get the speaker positioned so that that coloration is at its minimum. Panel speakers, though, do have great thing going for them with their dispersion. Because if you think about it, a panel is a dipole. So, as you move off to the side, the output falls to a null when you're exactly 90 degrees off axis. If you look at my quad review in the May issue, you can see that. You're not going to get any energy coming off the sidewall, or the ceiling, or the floor at that point, just because they're in the null of the speaker. And so they have a different set of problems, but in some ways they're easier to set up in rooms than a conventional speaker because of that. So,
When you take the measurements that you were showing for an impulse response and individual drivers,
yeah.
how do you actually perform that? Do you open the cabinet enough to be able to drive it?
No, I mean, I do it when you have a speaker which is bi-wired. Oh, where's my slide? Yeah, so here's the step response of that typical speaker. And basically, this was a tri-wired speaker, had 3 sets of terminals, so I could just look at each individually. It's tricky getting inside speakers. I tend not to do it, because then I have to return the speaker undamaged in manufacture. So in this case, it was tri-wired. I could show the overall response, the tweeter response, mid-range response, woofer response. But then after a while, after you've been doing it for a while, and you look at step responses, you can say, oh yes, there we are. Without even looking at them individually. I know that's the tweeter, I know that's the mid-range, I know that's the woofer.
What can you say? Oh, go ahead.
Sorry.
So Consumer Reports has an interesting way of looking at things. As much as I like Consumer Reports from both sides, loudspeakers, what they would do is measure frequency response. I was wondering if you knew how they did it. But what they would do is give a cumulative score based on divergence above and below an ideal flat plot, and then you give that speaker a score it comes back.
Yes, that's what I meant by measurements being subjective. That choice of the flat plot, the perfect plot, is completely arbitrary based on their own.
But wouldn't it be, you could have a speaker that's fairly flat and lots of little bumps along the way, versus a speaker that has a giant suck out and a giant,
Yeah. Floyd Tall's work showed that the smoother the on-axis response and the smoother the in-room response, people will prefer it. If there are gullies in either the on-axis response or the dispersion, that speaker will tend not to be preferred. The ear picks up on it. What Consumer Reports does, or did, I don't know about now, they measure their speakers in room, and they have a target curve based on the mix of the direct sound and the reverberant field in the room, similar to what I do there in this response. and then they look at departures from it. But I mean, which is the better speaker here? It's very difficult. In the treble, once you go over these steps in the low treble, they're actually relatively similar. It's a little less, the red one has a little less energy there, whereas the blue one has a little more energy, but they're relatively good. But notice they do slope down with frequency. So which is better? Hard to say. You want the target which does slope down with frequency because in your room, the room furnishings are more absorbent the higher the frequency. So if you have a flat response in room, that will sound really tilted up because what you're doing is compensating for the absorption in your room with the response of the speaker. It will sound bright and tilted up. Low frequencies, it's difficult because they all have various characteristics interaction with the room. But I would say that looking at this from the uniformity of this response, the blue speaker is better. But it's an arbitrary choice on my part. And I think what Consumer Reports does, which is actually codifying that subjective decision, can be misleading because you'll end up with a speaker which actually they give a higher score to, which sounds worse.
Right. So the blue is the LS.
358.
And what's the red?
I don't want to say. Well, if I remember correctly, it's the audience 2+2. But yeah, you'd have to look at the reviews on the magazine. I'm not quite sure if it was audience. It may have been the teal TCS4. They actually had similar in-room responses. Did I say that? I didn't say that. Forget what I just said. They were two very good, well-regarded speakers. So,
What is your reference speaker?
my reference speaker?
Yeah, you are right to say my reference speaker.
Okay, the best speaker, I don't own a pair of reference speakers right now because I'm still looking. The best speakers I've had in my system ever were the Quad 2805 that I reviewed in May, given that it doesn't play rock and roll very well. The Revel Ultimate Salon 2, which did everything well, and I wanted to buy, except I had to choose between paying for my daughter to go to NYU or buying those speakers. And my family was not very cooperative. My child's education was more important. I mean, what? A long time, for many years, I used the B&W Silver Signature, which is this speaker, because I could get it to sound wonderful in my old listening room when I lived in Santa Fe, New Mexico. However, it doesn't have enough bass in my current room in Brooklyn. So I still have them, and I get them out every now and again. They still sound wonderful, but they don't have enough bass. And that's purely because I could get them to integrate, I could get them to work well with my old listening room, and I cannot get them to work well with my current room. The other 358s, I've had since 1978, and yes, they sound a bit nasal, and yes, they sound a bit bright, and no, they don't have any low bass, really, even though in the in-room shop, they have more than that reflex speaker. And every now and again, I drag them out, and I played them recently to my assistant, Stephen Mejias, who'd never heard them, and he didn't know anything about them. He's only 33 years old, he knows nothing old. So we've sitting down, I have them all hooked on Class A 600 watt monos, I have Class A preamp DAC, really high-end system. And he was saying, he was going, wow, these rock speakers rock, what are they? I said, well, they were from before you were born, Stephen. The Rogers Ellis 358s. He said, well, they're great. Why don't they make them anymore? I said, well, you know, they're not that good. But the point is, if you hang them on a system with really good amplification and source, they still are up to the task. And I use them as my reference for measurements. Every time I measure speakers, I tend to do 3 or 4 or 5 speakers at a time because it involves a lot of setting up, and, you know, as you saw from the photo in my backyard. But I always measure those Rogers at the same time to see how their performance changes, and also as a check to make sure I have the mic preamps turned on, you know. And they've been remarkably consistent over the years. You know, I have many, many measurements of those speakers, all showing that they don't change over time. So in that sense, they are a long-term reference. So,
I have a very narrow question, but I appreciate your comment. I have multiple large electrostatic speakers, 4 feet by 8 feet. And I read something from Dan D'Agostino once, which caused me to change the frequency response level. And that is, in a classic cone speaker, the radiating area reduces with decrease in frequency.
Yeah,
In a panel speaker, that's not true.
it's kind of true.
So the bottom line is, I've shaped the frequency response to decrease to 3 dB per octave,
Yeah.
which sounds the most accurate to me.
It's not always true. I mean, if you have a metal cone, reason people like metal cones and metal domes is their radiating area stays constant with frequency until they then have their fundamental resonance, in which they go crazy.
Yes.
But with pulp cones, yes, the breakup modes tend to operate so that the actual part producing the sound gets smaller as you go up in frequency. But it's a relatively uncontrolled manner, and it's going to depend on whether the speaker drive unit designer on how successfully they've managed to do that or not. It's so, yeah, in broad sense, Dan D'Agostino is correct, but in a detailed sense, yeah, there are exceptions.
But the perception is that it's flat.
Yeah.
It measured 3 dB.
Yeah, well, if it sounds flat, then, as I said, it is. If it sounds right, it is right, regardless of the measurements.
What can you say about how baffle width affects the sound of speakers? And, 30 years ago we had wide baffle speakers. Now we have a lot of narrow.
Well, you're basically playing with the dispersion. You're also playing with the frequency response. That if you have a speaker without a baffle at all, then its output is going to, as you go down in frequency, as you go up in frequency, its output increases. If you add a baffle, you can smooth that out. But it's a tricky one, because the larger the baffle, the greater the effect of reflections from the edges of the baffle. The smaller the baffle, then the more problems you have with the rising response in the mid-range. So you're balancing that. One thing I've always found is that speakers which have a baffle around the size of a human head, like the Rogers LS358, actually sound very natural in voice. And maybe it's because the dispersion is very similar to a real head, that of a real voice. I'm not sure, though, if that is scientifically valid or not. But certainly it's something I've observed over the years. And of course, we do get a wonderful property of a small baffle, which is that you have inherently very wide dispersion, and even dispersion, which gives you good stereo imaging, good, stable, accurate stereo imaging. I mean, if you want to judge imaging, the easiest way is to play your pink noise. And you just sit in your listening seat and you listen. You ask yourself, how narrow is that in pink noise sound? The same signal is coming out of both speakers. Psychoacoustically, your brain reconstructs that phantom center image. And it should be infinitely narrow at all frequencies. With almost all speakers, that's not going to be the case. At some frequencies, it's going to splash to the side, particularly if there are resonances present. Or if you have crossover problems in the speaker, it's going to sound a bit vague and diffuse at some frequencies. If your speakers are out of phase or another, it'll sound vague and diffuse at all frequencies. So you just sit and listen, and you know what the target is, infinitely narrow. How does it differ? And small speakers will inherently give you more stable, more accurate imaging and narrower central image of pink noise, if they're well designed. And a large speaker, a large moving coil speaker, not a panel, will give you have more difficulty getting that target towards that target. It's just the way it is. I'm always puzzled by the fact that you can use. It's not music, but it does contain all musical frequencies, and you can predict something about speaker performance from just listening in that way. I put a lot of on our stereophile test CDs. I did this one. Let me see if I quickly open this file and find it. I put pink noise. I put a lot of diagnostic things. So maybe do things by ear. I don't have it. I put on the Editor's Choice CD and on Test CD 2 a step tone burst. It goes from low C, 32 Hertz, goes all the way up to the C at around 4K and back down again. And it's in musical half steps. And just goes bom, 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 bom. It's a great diagnostic signal. You can hear cabinet resonances, you can hear room resonances, you can hear crossover problems, because all it is a musical scale. And you hear it sweep up, you hear it sweep down. And immediately you go, oh, I hear that, I hear that, I hear that. I always use it in my own speaker measurements, and I've asked a lot of people, why don't you use it? Oh, it's not music. Well, it doesn't matter, it's not music. It still has all the musical information. And if there's a resonance, a strong resonance in the speaker cabinet, which falls between one of those musical steps, there's a good chance it doesn't matter. You know, that piano, I'll play you a piano recording just because it's so pathologically horrible. As I said, it really is like somebody playing a xylophone along with the music. It's not exciting resonance now. And here it comes again. You can hear those notes jumping out. And it's not hard to hear stuff like that once you listen out for it. How are we doing on time?
We have time for perhaps one or two more questions.
Okay, so
I have an interesting set of speakers that I'd like to hear some feedback on. Typically a speaker, like you're measuring direct sound versus the sound that's reverberating in the room. One of the sets of speakers that I have actually has a mid-bass woofer, a mid-range, and a tweeter mounted horizontally, so that it's omnidirectional, fills the room, and it's almost counting on the reverberation of the room in order for you to hear the music. How does that generally differ with regard to the quality of the sound from the standpoint of the technical aspect?
Well, I'd be surprised if you got good stereo imaging from it.
Well, you really don't. It's so omnidirectional that you really don't get a
Yeah, because you're waiting, as I said, the sound you hear is a combination of the direct sound from the speaker and the reflections of that sound from the boundaries and the room reverb. And what that kind of design does is basically accentuate the effect of the reverberation. And it makes sure that the reverberant field is uniform and flat, at least up to mid-treble when it will start rolling off, just because of the increased absorptivity of the furnishings. So what you're doing is saying, well, if I sacrifice stereo imaging, I can get smooth perceived sound power. And that is a design approach which is valid if that trade-off is what people will like. I mean, all speaker designs involve trade-offs. I really don't like huge speakers unless they're very expensive, because if you have a big speaker, it has big panels, and an old kind of saying in audio, big speakers can have big problems. And if you make a speaker, if you decide, well, if I take a speaker and I'll live with it not going below 40 Hertz, like the BMW Silver Signature, you can make the cabinet smaller, which means the cabinet for a given cost can be a lot stiffer, which will push up the frequency of the cabinet resonances perhaps to a point where they'll either decay very quickly or they'll be high enough in frequency that they'll between the gaps in the music. So everything else then can be much, much better. So the price for price than a big speaker which has problems which cannot be solved without making it a lot more expensive. So all speaker designs are trade-offs between those kind of things. Do I sacrifice imaging precision, get smooth sound power, which is your speakers have done? Or do I sacrifice bass extension to get a much less coloured mid-range and a much better behaved cabinet, as with the BMW Silver Signature, which is what I prefer for a long time. I mean, you have to examine, when you're choosing speakers, people say, what's the best speaker? Well, there is no best speaker, because it's going to depend on whether there's a match between what you want and desire and what you need, and what the speaker designer has decided to throw away to achieve excellence somewhere else. Which is why we have so many speakers in recommended components.
Another interesting design aspect of the speaker system is that the subwoofers are in separate cabinets.
Yeah.
So there's a mid-bass woofer and a mid-range and a tweeter in a satellite cabinet that's
Yeah.
actually relatively small.
it's difficult to get ultimate integration between separate subwoofers and main speakers. Until it puzzled me that inexpensive speakers have separate subwoofers, because getting that integration perfect is extremely difficult, I have found.
I'm actually crossover over.
Well,
He's done a superb job.
okay.
We need to wrap up the formal part of the presentation today, so thank you very much, John, for being here.
Well, thank you. Had a great show. This looks like it's going to be a terrific show. Thank
And
you.
if John comes into the room, make sure you get up and let him sit down.
And remember to read the magazine.
Thank you, everyone.